a rectangular shaft on the torsions. And this one in particular, I would say high aspect ratio. So that means the cross section of this rectangular shaft is something like this one. Okay, and that means very thin, very long. And I think this one will help us to make a good approximations, the good simplifications of the membrane theory here. Okay. So we consider such a rectangular shape, and let me give the coordinate systems. And here, let me say, using x is here and y is here. Okay. So still using the right-hand rule, xy directions here. And to analyze, to use the membrane analogy to help us analyze these problems. Again, we could solve the Prandtl stretch functions by dealing with this equation. And we could use the first approach, and that is the Saint-Venant warping function. Okay. Besides the two methods, this could be the third one. And here, let me present. The third one, again, is to borrow this advantage. So to use this one, we simply mimic the cross sections of the shaft to the metal ring. So here, I'm going to, based upon, start with the membranes and to do this one. So assuming this is the metal ring, and then we put the membrane, we put the soap film onto it. So this is the top view. Okay, the soap film basically filled up here. So from the bottom side view here. So this is this is top view, and this is side view. Okay, so this is the metal ring here. Okay, so let me say this metal ring fixed again somewhere. So say you hold it, there's the stick, you just hold it. Okay, so initially without any pressure, the membrane is flat because of the tension. For soap film, for our case plane, that basically is surface tension of the soap you play with, right? Okay. So now we apply the pressures here to deflect the membrane, and in my note I used membrane is bulged. And in this way, for this case, the bulge is something like, in theory, would be something, don't draw it, okay, I'm going to something like this one, right, in theory. But again, here we consider is a very high aspect ratio. So as long as we keep that dimensions very large, the aspect ratio of the dimension very large, so in theory, along the middle side, the membrane, because membrane is very thin material, this side will be curved closer to the supporting side. But toward the middle one, that's going to become flat again. And that is due to the equilibrium of tension. We can prove it, but here let me keep not proving, and then let me just take the flat. Toward the middle side, that's going to appear as a flat. This one will happen only when there's a high aspect ratio of this geometry. If not has aspect ratio, for example, if the sides are very similar in length, then here we should assume that it's kind of more like parabolic. Good? Okay. Another side, from this side view, again, that is the stick we hold it. From this side, basically the shape of the membrane will be, let me use this one. Like this one. Okay, let me use the red one to indicate the profile. something like this. Okay. Those profile we can obtain from our Gaussian equations here. So here is what we did. So in this case, this is the top view, so this is side view, let me label it. So this is our y directions, and x, y, z, so this is our z directions. Okay, let me label the coordinate first. So this is our x directions, so this is our z directions. Okay. In this portion, roughly, in this domain, we can do approximations. The profile of the deformed membrane pretty flat, so that means deflections is pretty uniform respect to y equal to 0. That means deflections, change in deflection in the y directions is almost 0. It's nearly 0 in this segment. Okay? So with these things, again, we stick with in this domain, we can approximate this one, the second term is gone. So it's partial square phi and partial x squared equal to minus p over s. Good? We do approximation. Again, here we focus in this domain. So for this case, we can solve for is analytical solutions, and this one is only single degree, the ordinary differential equations. So therefore, this one is equal to solve for this one is minus p s and x squared. I don't know how to do this one here. I'm kidding. So whatever. Okay, you don't need to follow me because here is a prompt. Something like this one. A, B are considered be resolved by appropriate boundary conditions, right? So the boundary conditions is this. This one equal to 0 at x equal to this one here. So where is x? X is this one. So basically you can see the diffraction from here. This is 0, this is here. We simply apply the 2 points as a boundary condition because here this is a function of x. We apply the boundary condition in respect to x. So from here we can obtain this one is a function of x, and that one is p, 2s, and h minus x squared. Good? Okay. So at least in this domain, from this viewpoint is flat. From this viewpoint is something like this one. So if you're going to look at from this view, its profile is like this. But this point, the peak point, pretty much uniform across from here to here. You want me to draw it? So basically, in 3-dimensional, it's something like this. So this is the 3-dimensional. So in this domain, so this is the domain we right now considers. Okay, so from here, that is pretty much like this. They have the same cross section. So the top, if we link the peak here, then the peak is pretty much the same height. That is the meaning of this shape. Good? Okay. You may ask me, are we going to concern about this portion? That is a local information. If you want to precisely to solve for this one, go ahead and by solving these partial geometry equations. I won't oppose, but again, here we're using the membrane analogy is to help us quickly grab the big pictures. So whatever the simple way, we go there first. That is this domain. Okay. So under these situations, we can do a lot of things. So the first one, with this one in place, then we can have the first result we can calculate is, for example, we can estimate the volume there. Okay, so basically this one, let me give dimension here. So say the whole dimension is B, and this dimensions is H. Okay. So given those dimensions, and then here, if we only approximate the volume here, so that is a volume pretty much, we're going to use that volume as approximation of the whole volume there. Okay, so this one basically is B times the X equal to okay, so this one is P over S and BH3 by 12. Okay, so this one is our volume. You can see in these calculations, I take the integral, I try to calculate the volume underneath the red curve by approximating and using this calculated, this one is only good for describing this portion. So basically the approximation has been done to approximate the site, the two kind of site. It's not so accurate, but we just take it. Good, okay. So here you should know where our approximation may kind of influence to our formulations. As much as how much you want to improve, we leave it. So that is this one. Okay. And on the other side, we have this analogy. T is analog to V. So which means from here, T is in analogy to 2V, okay? And what is V? Here is our analog symbols, okay? So here our calculation is 2 and V equal to this one, P over S and BH3 12, okay? And then I'm going to make quite a big analogies. So what is P over S? P over S, I reverse it. So P over S basically is in analogy to 2G beta. So here I use analogy. So I'm kind of jumping around from the making analogy or from our result. Okay, so that is 2G beta. Okay, so this, let me keep writing. Okay, so this result give us is G beta 3B H cubed. So in this way, from taking the analogy, and we can see T leading to this portion here. This one, BH3 divided by 3, and we can say that is called the, earlier I named it polar moment inertia, and the beta term is called the torsional constant. So I think I made a mistake in the previous lectures, and for all the terms I have said polar moment inertia, that should be corrected by, replaced by torsional constant. The reason why the torsional constant is different, is larger than polar moment inertia. For circular shaft, that by chance, they two are just equal. The explanations are given in the handout I emailed to everyone Friday last week. Okay, if any questions, wait for finish this section. Okay, jump back to you. We good? Okay. So under these situations, then that is the first one we have. The second one we come up with is we can estimate the stress. For example, YZ in proportions, YZ is in proportion is this one minus B and X. Okay, this one in terms of our calculations, and that one is P over S times X. Okay, so and again the P, this one is in terms of 2G beta. Okay, so therefore tau YZ and equal to 2G beta X, and then plug in those informations. For example, let me say this one is our definition J. So from here, we can have beta equal to T over G J. Okay, so introducing the torsional constant as J, then we have beta like this. So here we can have 2G beta equal to 2T over GJ X. So this one is 2T over J X. So this is tau YZ. Okay. And so tau YZ, what is that one? Tau YZ is an analogy to this one. So let me plot at this moment, let me plot the contour. So the contour of the membrane diffraction is something like this. My drawing is not so precise, but you know what I mean. Okay. So something like this one. And from here you can see what is meaning of this one. So that is means the change in diffractions. You see this one. Sorry, using this notation. Okay. The change in the diffraction of the membrane across the x directions. So that should be this line here. Okay, so basically, we look at in x direction, you can see the gradient in this direction is much larger than the gradient in this direction, right? Again, the gradient, the closer the distribution, that means the larger gradient. The larger gradient, that means the larger stress. So basically here, let me highlight here and here. That is where the larger shear stress could occur. And more precisely, from here you can see the maximum tau YZ maximum is happened when x equal to h over 2 here. Okay, so that means here I can indicate the maximum is here. Okay. Good. In this case, our another stress component, xd, another stress component, xd, is proportional to this one. In our analysis, we study in the this portion that is 0 in our approximation. So in this approximation, this one is 0 here. Again, this approximation is only valid in this domain, Okay, approaching to the boundary, then that we do need a little bit more detailed calculation. But as long as in the middle one, we are good. Okay. Good. Everything right now we can more quantitatively solve for this one. And from this case, we come up with very important result. And from that one, I can illuminate this portion here. So basically, that one tells us is this: if we have a shaft with such a cross-sectional shape. This is B, this is H. B over H is very large. Then the torsional constant. Okay, basically that can be described as 3 and B, H, 3. Okay, so that is the number for this one. If you go to check against our tables, and when approaching to large, that formula is the one we have been through. The indications, the biggest indications of this formula is this. You see, this one is totally purely geometric. So, which means if we would have the shaft, let me make up one here. I exaggerate. If we would have the shaft with a cross section like this, how can you calculate or make a good approximation of the torsional constant for this? Easy. You simply you split into the combination of this pattern. If you split in this or in this, I don't care. Only small pieces there, I don't care. So for this one, how about you say this is B1, this is H1, and the lower side is B2, this is H2. For this case, that's simply a summation of this piece plus this piece. So for this one, that is 3 B1 H1 3 plus 3 B2 H2 3. If you have additional more pieces, you simply continue to decompose into the fundamental, this pattern, and keep adding it. Good? Okay. The last one I want to share with you is this. In topology, we can have the shape like this, rectangular angle. Can we make in topology like this? This has the uniform thickness, and here we simply use a rectangle cross section, we curve it into this one. Okay, the same thing, how to calculate this one? The same thing, if you are able to measure this length, so let me say this radius is R. Okay, so basically here, the B, you can see B equal to 2 pi R, right? And let me say this T is thickness, so this one will be 3 times B H cubed, that will be equal to 2 pi R times T to the cube, right? Similar to topology to this one. Good? Good? So this is a torsional constant. If I have a different shaft, and this shaft is like this, let me say the R, the thickness T, T is uniform. If I have another shaft, this is a hollow shaft. This shaft is different from this because here we have a small cut. Okay, and let me say this space is almost 0. Are you able to calculate the torsional constant for this? That simply is our polynomial inertia, right? So that one is pi over 2, if you remember outer radius to the force minus the inner radius, that is this one. Okay. Compared to the two numbers, they basically made of the same material. Let me ask, which shaft can carry more torsion? which means in terms of the practical applications, which shaft is stronger. That will depend on their torsional constant. Good? Okay, the answer is this one. This will carry, given the same material, this will able to carry more torsion before failing. Okay, the reason why you can do a little bit more the derivations, but that end up our lectures today.